This is Grommet. He is the best cat in the whole wide world, and I miss him. His hobbies include sleeping on the veranda and sleeping on his humans. Holy cow, this photo is 10 years old. Here he is supervising me writing my thesis. Here he looks worried because I'm applying for a job on the other side of the continent. And here he looks dischuffed because I'm buying plane tickets to move for that job. For a while now, I've been meaning to try to take the Fourier transform of a photo of Grommet, partly as an exercise and partly because of this xkcd comic. A Fourier transform decomposes a signal into the frequencies that make it up. For example, a square wave is made by superimposing harmonically related sine waves. Applying a Fourier transform to the square wave tells you the frequencies and amplitudes of the individual sine waves that make it up. Fourier transforms can also be applied to images. Here's a simple example. The Fourier transform of this image is a series of points describing the frequency and direction of the stripes. Similarly, these horizontal stripes transform into a vertical set of points. The orientation of the points represents the direction of the stripes, and their distance from the center of the image represents their frequency. All images can be broken down into a set of contributing frequencies in this way, and you can use lots of different software to do it, like R, Python or MacLeod, but for this I'm going to use Mathematica. First, I need to import my image. Then I just need to prepare the image data for the software. You can pause the video if you want to see exactly how I'm doing this. And now I'm ready to take the Fourier transform. This is the magnitude spectrum. It shows what frequencies in what amounts are present in the image. This vertical band shows the top to bottom differentiation of the photo, while the horizontal band represents the right to left detail. These faint diagonal bands will be due to angled elements in the photo, such as Grommet's paws, ears and whiskers, and the texture of the carpet. This is the phase information from the photo. In a slightly oversimplified explanation, the phase information tells you where in the image the corresponding frequencies appear. Again, the phase clearly shows the vertical and horizontal differentiation of the photo. Right, done. I've succeeded in taking the Fourier transform of my cat. But there are some fun things I want to try. By obliterating some parts of the Fourier transform, I can reconstruct the image with certain frequencies missing and see what effect this has. This is essentially the basics of image processing. So what I've done here is I have removed frequencies in all directions above a certain value. This is called low-pass filtering. Now, if I reconstruct the image, you can see that I still get a reasonably clear photo of Grommet. But if you look closely, sharp edges and the texture of the carpet are blurry, and Grommet has started to lose detail in his fur and whiskers because I've removed the high frequencies that encode this information. This is one basic way in which image compression is done. You can see how much information I removed compared with how little it degraded the image. You could remove half of the information from the Fourier transform and not really see much of a difference in the image. Now let's try removing the low frequencies and see what happens. Here's the magnitude spectrum with the frequencies that made up the previous image of Grommet deleted. And here's what he looks like. Only the sharp features remain. You can see his whiskers and the detail in his fur. The specks all through the background are the texture of the carpet. So you can see that for most photos of people and animals, the low frequencies matter more than the high frequencies. I still think he's adorable even when you high-pass filter him.